Welcome you all to another video session on the use of finite element procedure for solving structural engineering problems. In my previous videos, I analyzed different types of one-dimensional structural problems. I'm done with that now, and in this video, I'm moving into another set of structural problems, the truss analysis. In this video and subsequent video, I'm going to analyze truss structural problem using the finite element procedure. I'm going to analyze plane truss problem. I'm going to analyze 3D truss problem. I'm going to analyze truss problem in which the loading is symmetric. In that, I'm going to teach you about the characteristics of symmetric loading on a symmetric truss. How you can reduce your truss by half by considering symmetry. I'm also going to talk about asymmetric loading in truss. I'm going to talk about the characteristics, and we're going to solve sample problem for symmetric loading and asymmetric loading on the Ansys program. Lastly, I'm also going to cover a type of plane truss a type of plane truss problem with inclined roller support. In that problem, we'll have to apply the multi-point constraint model, which I've already introduced to you in one-dimensional analysis in my previous one-dimensional YouTube video. We're going to look into how we can apply the multi-point constraint model to solve problem with inclined roller support. So I'm going to start the lecture now. If you see the title is actually called, the title of this lesson is stiffness matrix method of 2D truss system using Matlab. The stiffness matrix method is very similar to the finite element procedure, so it actually does not matter. The stiffness matrix method is finite element procedure. Simple as that. So that's why I'm using this PowerPoint presentation in teaching you finite element procedure applied to truss problem. So you don't need to be bothered with this title. You can look at it as finite element procedure of solving 2D truss system using Matlab. In this tutorial, we're going to solve a plane truss system using the finite element procedure by using the penalty approach. But unlike the one-dimensional problem, I'm not going to add the normal large stiffness, which is equals to the greatest value in the stiffness matrix in the global stiffness matrix multiplied by 10,000. Using Matlab, I'm going to add a very, very large stiffness called infinity in Matlab to denote our large stiffness. This is another procedure of solving truss problem using the finite element procedure. This procedure, I've not actually found it in any textbook where they add infinity value to the support degree of freedom in the global stiffness matrix. In the global stiffness matrix for truss system. So we are going to add a value in Matlab called infinity to the support degree of freedom at the diagonals of the global stiffness matrix. In my next video, I'm going to solve this same problem the normal way by penalty approach. That is using a large stiffness, which is the greatest value in the global stiffness matrix multiplied by 10,000. But in this video, I want to show you a neat and alternate way of solving solving truss system using the finite element procedure by penalty approach. You will find it very interesting. I promise you that. So this is the problem that we are going to solve. The problem is actually, if you look at it can be defined as a cantilever truss that is 4 meter long and 1 meter deep. There are 3 point loads on the truss. And if you look at it, the truss is both statically indeterminate, is externally indeterminate, and statically is externally indeterminate and internally indeterminate. Internally indeterminate, it has two redundant members. And external determinacy, it has more than 3 reactions. There are 4 reactions for this problem. We have 2 reactions at this node and 2 reactions at this node. So the minimum we need is 3, and we have 1 SS. So it is one. It is one. It has one. It is externally indeterminate by 1, and is internally indeterminate by 2 redundant members. The material property of this truss or the member, the cross-sectional area is 20.7 times 10⁻⁴ meters square. The Young modulus is 205 gigapascal. This can also be denoted as 205 gigapascal. So to solve such problem using the finite element procedure, like the one-dimensional problem, which has its own local stiffness matrix, the truss element also has its own local stiffness matrix. For truss element, the local stiffness matrix is defined as this. The local stiffness matrix is defined as this. The local stiffness matrix K is equals to the cross-sectional area of the member times the Young modulus divided by L multiplied by this matrix. This theta is an angle between the horizontal axis and the member. I'm going to define it. So the local stiffness matrix is defined by this. And to define this angle theta K, assuming we have a truss element with node number 1 and 2, degree of freedom 1, 2, 3, 4, and the labeling of the member K, length K. There is something I didn't depict on this diagram, which is very important. And when we are defining truss member, it is very important we denote an arrow. That arrow denotes, like, either you denote the arrow like this, pointing from node 1 to node 2, or you denote an arrow pointing from node 2 to node 3. This arrow pointing from node 1 to node 2, it means that node 1 is our start node and node 2 is our end node. For this problem, the arrow pointing from node 2 to node 1 means node 2 is our start node and node 1 is our end node. So to define theta is always measured from the start node. So for this problem here, because the start node is node 1, we measure theta K from node 1. And theta K is the angle between the horizontal x-axis and the member. For this problem, our theta K is measured from node 2 because the arrow points from node 2. So theta K is measured from the horizontal x-axis to the member counterclockwise. So that's how theta K is specified. This is how theta K is specified. For this problem here, if we take this as theta K, that means our numbering for the for our local stiffness matrix, which is something like this, will be 1, 2, 3, 4, 1, 2, 3, 4. But if we are using this, if we are defining if we are defining our member with this angle at node 2, that means we have to the numbering for this matrix will be 3, 4, 1, 2. You know, 3, 4, 1, 2, 3, 4, 1, 2. You always take the horizontal numbering first before the vertical numbering. 3, 4, 1, 2. 3, 4, 1, 2. 3, 4, 1, 2. 3, 4, 1, 2. So anyhow you define this member, they are both correct. But it's important that you stick to a notation. If you are using this direction, that means you stick to this notation. If you are using this direction, you stick to this notation to the end of the problem. So this is very important. This is the most important aspect of analyzing source problem using the finite element procedure. I hope you understand all this. So I will repeat myself. This is the local stiffness matrix for source, which can also be written like this. It's blank here. This is either with for a member source element k. If the arrow is pointing from node 1 to node 2, it means that the degree of freedom numbering will be will be 1, 2 from the start node 1, 2, 3, 4. But when the arrow is pointing from node 2, the number of the degree of freedom for the matrix will be 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. So this is very important. This blank here is for cos squared theta k. This blank here is for cos theta k sin theta k. So this is just for illustration. So this is the most important aspect of solving source problem with finite element procedure. If you understand this aspect, solving this problem with finite element procedure is very, very easy on Matlab. I'll move to the next slide now. So again, this is the local stiffness matrix for its source. On Matlab, I wrote a function. On Matlab, I wrote a function that can easily compute the local stiffness matrix for an element, giving input variable of theta, L for length, E for Young modulus, and A. So if I should input these 4 parameters in this function, Matlab helps me compute my local stiffness matrix. For example, so the name of the function is called GSME. The name of the function is called GSME. The name of the function is called GSME. So on Matlab, I can say on the command window, I can say K1, my local stiffness. I can turn my local stiffness matrix K1, my local stiffness matrix K1, and use this function GSME, and enter 4 parameters, and my local stiffness matrix is automatically calculated with the Matlab software using the function which I defined on my Matlab program. I will illustrate this now on Matlab so that you understand this properly. So this is the function I wrote on Matlab to compute the local stiffness matrix for me. So I define the function as a GSME. So once I enter these 4 inputs variable, theta, that is the angle that defines my truss finite element. L is the length of my member truss element. E is the Young modulus. A is the area. So once I compute this, and the function computes cos theta for me and stores it in C, a variable which it stores the cos theta in a variable called C, and it also stores sin theta in a variable called S. And it computes the local stiffness metric defined by this line of code. And C multiplied by C is like the cos squared theta. C multiplied by S is the cos theta sin theta. Minus C multiplied by C is the minus cos squared theta, in that order. So multiplied by E, this matrix is multiplied by E multiplied by area divided by L. So I can, in the command line, I can say K1 equals to GSM. I enter say 30 degree as the theta, length say 500 millimeter, that's 5 meter. Young modulus say 200 gigapascal. 200 gigapascal. I like working in Newton per millimeter square, so 200 times 1000 Newton per millimeter square. The area say 50 times 50 mm by 50 mm cross section. That is 2500 mm squared, the cross-sectional area. So if I should run this, you see Matlab computes my K1 for me, my local stiffness matrix for me. So I use in my Matlab program, I use this function to compute all my local stiffness matrix. It makes computation of the local stiffness matrix very easy, just by entering your 4 parameter in the function. So now we'll go back to PowerPoint. This is how this function works on the Matlab. It's a function I created to compute the local stiffness matrix. I'll move to the next slide now. Important formulas you need to note about finite element procedure for 2D truss problem. For us to compute the displacement quantity for truss elements, we can use this formula. ds is denoting the global stiffness matrix. ds is denoting the displacement, the global displacement vector, the displacement matrix. Ks is the global stiffness matrix, the modified global stiffness matrix. Ps is our global force vector. So when we invert the global stiffness matrix and we multiply it by the force vector, we get our global displacement matrix. So this formula is very important. And if we want to compute the area force for each member, we can also use this formula, where Pk is the area force vector for each element. For element 1, say Pk, say P1, for this k is 1. If the element is labeled 1, it will be P1, is equals to K1 multiplied by ds1. This k here is the local stiffness matrix of the truss element, while dsk is the local displacement vector. I'm going to explain how these matrices and vector look like on Matlab in my next slides. So be patient, you will understand how to use this formula. This is for the global stiffness matrix, while this is for the local stiffness matrix. So you should note this. So this is our truss problem. To solve this problem, the first thing we need to do, we need to label each truss element. We need to label the nodes of our truss system, and we also need to signify the direction of each truss element. For the labeling of each truss element, I label each element using a green triangle. You can see it. You can see this on the slide. So this truss system has 11 truss elements, which I labeled element 1, element 2, element 3, element 3, element 4, element 5, 6, 7, 8, 9, 10, 11. This labeling can be in any order you like. It does not matter how you label it. I choose to label my truss element in this order. But once you label it in a particular order, you have to stick to it to the end. So once you have labeled the truss element, the next thing you do, you need to number your node. The number of nodes can also be in any order. In this problem, I define this node as my node 1. I define this node as my node 2. I define this node as my node 3. I define this node as my node 4. I define this node as my node 5. And I also define this node as my node 6. Each node, so that is how you label the node. So in this problem has 6 nodes. So after you have labeled the nodes of your structural system, the next thing you need to do, you need to label or number your degree of freedom. And for a truss element, each node, unlike the one-dimensional problem, in which each node has 1 degree of freedom, the truss system has 2 degrees of freedom. Like node 1 has 2 degrees of freedom, degree of freedom 1 and degree of freedom 2. We can see here that the degree of freedom 1 is pointing in the horizontal direction and the degree of freedom 2 is pointing in the vertical direction. You should always number the degree of freedom in the horizontal direction at a node first before the vertical degree of freedom. This is good practice. And when you are numbering the degree of freedom, it is advisable you label the degree of freedom in ascending order of node numbering. Like node 1 has 2 degrees of freedom. So I label the horizontal degree of freedom 1, I label the vertical degree of freedom 2. I move to node 2 and I label the horizontal degree of freedom 3 in the horizontal direction 3 and the vertical degree of freedom 4. If you notice, I don't come to node 4 and label node 4, 3 and 4. I'm moving in ascending number of node numbering. 3 has 2 degrees of freedom, so 5 and 6. I move to node 4, 2 degrees of freedom 7 and 8. I move to node 5, 2 degrees of freedom 9 and 10. I move to node 6, 2 degrees of freedom 11 and 12. So this problem has 12 degrees of freedom. So we need to define, this is how we define our truss system, our finite element model for the truss system. And when we are using the finite element procedure to solve truss problem, we label the member, we label the node, and we also label the degree of freedom at each node. So I hope this is well understood. I will move to the next slide now. My next slide, it will be explanation of this procedure on Matlab. So I'm going to explain this procedure first on PowerPoint before I go to Matlab, so that you understand it properly. Going to front. So, well, after we have defined our finite element model for the truss, the next thing we need to do is to compute the local stiffness matrix for each member. This problem has 11 members. That means we need to compute 11 11 local stiffness matrices because the problem has 11 members. So I denoted K1 as the local stiffness matrix for K1, and I computed it using the GSME function which I talked about earlier on. So for you to use this function, first we need to define our Young modulus. For this problem, the Young modulus is 205 gigapascal. I've said that already. The area is 20.7 times 10 minus 4 meters square. So I define E here is denoting my Young modulus, 205 times 10 power 3 Newton per millimeter square. My units, I'm using a unit of Newton for my force and for the length millimeter. So that's why I multiply by 1000. So this is 205 times 10 power 3 Newton per millimeter square. The area is given by this 20.7 times 10 minus 4 times 10 power 6 millimeter square. This times 10 power 6 converts this area, which is the meter square, to millimeter square. So I compute my Young modulus. The A is denoting the cross-sectional area of my truss element. The theta for the first truss element is denoted as 0. Why is it 0? I will show you why it is 0. In my problem, this is my truss 1. Oh, I didn't talk about something. You also need to denote the direction of your arrow, which is very important when you are defining your truss model. So for this problem, you can see red arrow. Like for element 1, I said I put an arrow pointing from node 1 to node 2. For element 2, we have this arrow definition pointing from node 2 to node 3. I can decide to change the orientation of the arrow to this direction, but I chose this direction. It depends on you. You can choose any direction. So I'm using this direction for my element 2. For element 3, I'm using this direction. For element 4, I'm using this direction. For element 5, I'm using this direction. For element 6, I'm using this direction. For element 7, I'm using this direction. In that manner. So for element 1, how do we define our theta for element 1? Since the direction we choose for element 1 is pointing from node 1 to node 2, that means we will measure our angle from node 1 of the element, because the arrow is pointing from node 1. And we can see that the element is completely horizontal. So the angle between the positive x axis and the member is 0 because this member is horizontal. So theta is 0. Also for element 2, because the arrow is pointing from node 2 to node 3, we will take measurement from node 2. The theta for element 2 is also 0. For element 3, the theta for element 3 is also 0, because we are going to take our measurement of theta from node 4. For element 4, the theta for element 4 is 0, because we are taking our angle measurement from node 5. Let me use my eraser to remove all this sketch. For node 5, because the arrow is pointing from node 1 to node 4, we take our measurement of our angle from node 1, and the angle is given by this. It's a 90 degree angle from the positive x-axis to the member. This angle measured in an anticlockwise direction. So the angle for member 5, according to my arrow direction, will be 90 degree. For element 6, the angle will be The angle is also 90 degree because, why is it 90 degree? Because the arrow points from node 2 to node 5. For element 7, because the arrow is pointing from node 3 to node 6, the angle measurement will also be 90 degree. 90 degree. For element 8, this element here, our arrow is pointing from node 2 to node 4. So we're taking measurement from node 2. So our angle definition for element 8 is given by this. From the horizontal axis to the member measured in an anticlockwise direction. So to be 90 plus this angle. And this angle is maybe arctan 2/1 or arctan 1/2 plus 90. So this is the angle we use to define element 8. Let me remove this. For element 9, for element 9, this element here, for element 9, the arrow is pointing from node 1 to node 5. So we take our measurement of angle from node 1, and the angle measurement is given by this. Arctan 1/2 is this angle here. For element 10, the arrow definition is pointing from node 3 to node 5. So our measurement of angle will be taken from node 3 because the arrow is pointing from node 3. And the angle will be defined by this. For element 11, the arrow is pointing from node 2 to node 6. So the angle will be defined by this. I hope this is perfectly understood. I explained each of the angles for each of the elements. I think it is perfectly understood. So we can see, you can see while we are defining the local stiffness matrix on Matlab, I defined θ1 as 0 degree because the angle is 0 degree. L1 is 2 meters from the question, 2000 mm, 2 meters. This dimension here. Oh, sorry. 2 meters, 2000 mm. Sorry. 2000 mm. L1 is the length of the member, 2000 mm. So once we define E, A, theta, and L1, we can input this variable in our function here. So K1 is equals to, you use this function which I created, GSME. You enter θ1, L1, E, and A. We see that Matlab compute our local stiffness matrix for element 1 for us. The same thing is done for element 2. Theta is also 0. L2 is 2 meters. As stated here, this is the length for member 2, 2000 mm. And K2 is formed by using this function and entering θ2 and L2 as input variable, θ2, L2, E, and A as input variable. So if this is done, this Matlab helps us compute our local stiffness matrix, which is given by this. One thing I want to explain before I leave here, let me use my eraser to erase all this. For this K1 matrix, because the arrow is pointing from node 1 to node 2, well, the numbering for the the numbering for the K1 matrix will be 1, 2, 3, 4 from the degree of freedom. This degree of freedom, this degree of freedom. Element 2 has 4 degree of freedom. So the number will be, because the arrow is pointing from 1 to 2, the number of the local stiffness matrix will be 1, 2, 3, 4. This is what I mean. So this will be 1, this will be row 1, this will be 2, this will be 3, this will be 3, this will be 4, this will be 1, this will be 2, this will be 2, oh, this is very bad. This will be 3, and this will be 4. For element 2, this is element 2 here. The element 2 has 4 degree of freedom too. This degree of freedom 3, 4, 5, 6. And because our arrow is pointing from node 2, the numbering of degree of freedom will start from the degree of freedom at node 2. So the number will be 3, 4, 5, 6. So this element 2 will be 3, 4. The number will be 3, 4, 5, 6. 3, 4, 5, 6. So that's how it's going to be. So let me explain this. Let me bring this to the front. For element 3, the theta is also 0. L3 is also 2000 mm. So you can compute the local stiffness method, which I term K3, by using this function. So K3 is formed. This is our K3 local stiffness matrix. So if we look at our definition for element 3, this is element 3 here. Element 3 has 4 degree of freedom, 7, 8, 9, 10. So the numbering, because the arrow is pointing from node 4, the number will be 7, 8, 9, 10. If the arrow is pointing from node 5, the number will be 9, 10, 7, 8. So you should be careful with this. The direction of the arrow is very, 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 very important. So because the arrow is pointing from node 4, my numbering is 7, 8, 9, 10. So here will be 7, element 3 will be 7, 8, 9, 10. 7, 8, 9, 10. Element 4 is also done the same way. The local stiffness matrix is formed, and we look at the degree of freedom for element 4. We look at it. This element 4. The degree of freedom for element 4 is this and this. And because the arrow is pointing from node 5, the number will be 9, 10, 11, 12. So you number the global stiffness matrix in this order. So this is very important too in finite element procedure, understanding how to number your global stiffness matrix. Also, this is also done for element 5, element 6, element 7, element 8. I'm only going to explain one of it because they are all the same. I think I should pick element 8 so you understand what I did there. I think it's a bit more complicated than the rest. So this is element 8. Our theta 8, our angle for element 8 is given by 90 plus r tan 2 over 1. This A tan D is a inbuilt Matlab function which is used to compute the arctan of an angle. So arctan of an angle. We are using arctan D. This D means what we put in this bracket must This D means what the output of our angle will be in degrees. That's what it means. If you are just using arc, there's another function called arctan, just arctan. That function returns the angle in radians. But because we are using arctan D, the angle that is computed is in degrees. So for element 8, let's check the angle definition for element 8. This is element 8, and the arrow is pointing from node 2 to node 5. This is the arrow here. So that means our angle is given by this. And this angle is 90. This is 90 plus this angle. So this angle is the arctan 2 over 1. 90 plus arctan 2 over 1. 2, this length, opposite of tan theta equals to opposite of adjacent. The opposite is 2 meters. The adjacent is 1 meter. 1 meter. So that's how we compute the angle. So on Matlab, this computes our theta 8, 90 plus arctan 2 over 1. This is the length of the member. This square root is also an inbuilt function in Matlab that computes the square root of that compute the square root of a number. So I use for element 8. For element 8, the x component is 2000 mm, the y component is 1000 mm. So we can compute the length of the line by using the line formula, square root of 2000 square plus the square root of 1000 square. So this Matlab line of code does that. So once we have computed theta and the length, we can now compute our local stiffness matrix using our GSME function. So once we run this code, the local stiffness matrix is computed for us and is defined in the variable called K8. So this is the local stiffness matrix, and the numbering will be, let me check, the numbering will be 3, 4, 7, and 8. Just want to give a thorough explanation so that everybody understands. Element 8, because the arrow is pointing from node 2 to node 4, element 8 has 4 degrees of freedom. 4, 3, and 7, 8. But because the arrow is pointing from node 2, the numbering is 3, 4, 7, 8. This is very important. So the numbering for element 8 will be 3, 4, 7, 8. 3, 4, 7, 8. So you do this for the 11 finite elements. You compute the local stiffness matrix, and you also note the numbering in this manner for each of the local stiffness matrices. So I did this for all the truss elements through element 11 in the same order. Then after we have computed the local stiffness matrix for all the elements, the next thing we need to do, we need to define a last stiffness to our support degree of freedom. For this question, for this problem, our support degree of freedom is at node 1 and node 4, because that's where we have our supports. As the degree of freedom at node 1 and node 4 are 1, 2, 7, and 8. It means that we have to define a large stiffness for this 4 degree of freedom. So it means that in the global stiffness matrix, 1, 1, we have to add a large stiffness to 1, 1. We also need to add a large stiffness to 2, 2 in the global stiffness matrix for this problem. And for position 7, 7, we need to add also a large stiffness. For 8, 8, we need to add a large stiffness. The value for this large stiffness in this lesson will be infinity. Let me show you what I mean. You can see at 1, 2, 7, I define a variable called K1R, K2R, K7R, K8R. These are the stiffness. This is the last stiffness I want to add along the diagonal at 1, 1, 2, 2, 7, 7, and 8, 8. Now, the stiffness I'm defining it as infinity. There is a variable in Matlab called infinity, a very large number. I don't know the number, but it's called infinity. So I'm adding a value called infinity at 1, 1, 2, 2, 7, 7, and 8, 8 of the local stiffness matrix. So I'm defining these stiffnesses here. So you can see that's why I say K1R equals to infinity, K2R equals to infinity, K7R equals to infinity, K8R equals to infinity. It's actually so long. So once we've defined the last stiffness for our support degree of freedom, we now need to compute our local stiffness matrix for the truss element. So like the one-dimensional problem, the first thing we do, we need to create a base matrix, a zero base matrix. In our truss problem, because we have 12 degree of freedom, from 1 to 12 degree of freedom, it means our zero matrix will be a 12 by 12 matrix. So I define our zero matrix as a 12 by 12 matrix with this Matlab line of code. You can see the 12 by 12 matrix defined as this. So K equals to zeros bracket 12. So you can see the 12 by 12 matrix. So once we have created the 12 by 12 matrix, the base matrix, the zero matrix, we need to add each of the local stiffness matrix to this base matrix. For element 1, which is defined as K1, I'm adding K1 to the zero matrix. And because element 1, let me send this to the back, sorry. I need to send this to the back. This is the local stiffness matrix for element 1. And you can see the numbering is 1, 2, 3, 4, 1, 2, 3, 4. Because element 1, which is here, is located between node 1 and node 2, and the degree of freedom at that point is 1, 2, 3, 4. So it means at this is actually what it means. It means in my zero matrix, I need to add the local stiffness matrix, which is a 4 by 4 matrix in this position. And this matrix, this line of code here does computes that for me. This one column 4 as along the row from 1 to 4, and along the column from 1 to 4, add K1 to it. So once we write the code in this manner, K1 gets added to this position in the zero matrix. So you can see our K1 matrix is defined by this. You can see at column 2 is 0, 0, at column 4 is 0, 0. So if we check what we added, you can see year 2 is also 0, 0, year 2 is also 0, 0. We only have value year, 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 and year. So this line of code adds K1 to our 0 matrix. We also need to add K2. For K2, I think I should copy this image to this position, so I don't need to be switching. For K2, this is K2 here, and the local stiffness matrix, the degree of freedom for element 2 is 3, 4, 5, and 6. The arrow is pointing from node 2 to node 3. So that means my numbering will be 3, 4, 5, and 6. So sorry, send to back. So if we should check this line of code, adding K2 to the 0 matrix, I'm adding it between at 3 to 6 of the global stiffness matrix, 3, 4, 5, and 6. This 3 column 6 means 3, 4, 5, and 6. Along the row, also along the column 3, 4, 5, and 6, 3 column 6 plus K2. So once you write the Matlab code in this manner, K2 gets added to the base matrix at this point, the 4 by 4 matrix at this point. So this is where K2 matrix gets added to in the global stiffness matrix. Remember, this is 3, this is 4, this is 5, this is 6. This is also 3, 4, 5, 6. So this is how it is done. This is how we add the local stiffness matrix to our base 0 matrix. Let me bring this forward. This is another one. This is for K3. Let me bring this forward. This is for K3. Element 3, because the arrow is pointing from node 4 to node 5, so the number will be 7, 8. The number will be 7, 8, 7, 8, 9, 10. 7, 8, 9, 10. So that's why the number here is 7, 7 column 10. 7 column 10 means from 7 to 10 along the row, comma 7 column 10 along the column, from 7, 8, 9, 10 along the column, adding 3 to it. Adding K3 to it, writing the code in this manner, so K3 will be added to the 0 matrix. Same thing for K4. We do the same. K4 is located bring to front. K4 is located between node 5 and node 6. The degree of freedom is 9, 10, 11, 12. So that's why it is 9 to 12 for K4. Let me copy this image, take it to the next slide to make my explanation easier. So for K5, element 5 is located between node 2 and node 4, and the degree of freedom number for that matrix will be 1, 2, 7, 8. So that's why I number it in this manner: 1 column 2, 7 column 8. because the numbering are not together like 1, 2, 3, 4, I have to break it into two. You should note this: 1 column 2 comma 7 column 8. You write this in square bracket, and you also write, so this is for the row, you also do for the column 2, and you add K5 to it. You do the same, you write what you write on the right hand side, you also write on the left hand side, and you add K5 to it. So this is how we add K5 to the zero base matrix. So 1, 2, 7 and 8. 1 column 2 comma 7 column 8. In a square bracket, open another square bracket, 1 column 2 comma 7 column 8. You close the square bracket, and you close the outer bracket again, equals to, you repeat what you wrote on the left hand side, you repeat it on the right hand side, and you add K5 to it. So if you write it in this manner, K5 will be added at appropriate location. For cases, that's element 6. Element 6 is located between node 2 and node 5. This is element 6 here. It's located between node 2 and node 5. The degree of freedom number will be 3, 4, 9, 10. 3, 4, 9, 10. So 3, 4, 9, 10. Let me send this to the back. 3, 4, 9, 10. I want to highlight 3, 4, 9, 10. This is 3, 3, 4. So this is one part of the matrix here. 3, 4, 3, 4. The 4 by 4 matrix, there are 16 elements. 3, 4, 3, 4. 3, 4, 9, 10. 3, 4, 9, 10. This is another part of it. 3, 4, 9, 10. The other, so I've highlighted eight elements in that matrix. The other parts I cannot view it because Matlab only shows 8 rows of the matrix. The 9, 10, 11, 12 is hidden. So I cannot view 9, 10, but it is actually there. So but I've highlighted like 8 elements in the local stiffness matrix of K6. So this is part of it, this is part of it. Going to front. For K8, K8 is located between going to front. K8, element 8 is located between node 2 and node 4. The degree of freedom numbering will be 3, 4, 7, 8. We're numbering in this manner because the arrow is pointing from node 2. So we're picking the degree of freedom at node 2 first. So 3, 4, 7, 8. So that's why we have 3, 4, 7, 8 in the Matlab code here, and we add K8 to the zero base matrix. So this is how you this is how you assemble the global stiffness matrix on Matlab. So I did this for all the local stiffness matrices till the 11th element, K11. So this is my final global stiffness matrix. So after we have assembled the local stiffness matrix in the global stiffness matrix, the next thing we need to do, we need to add a last stiffness at our support degree of freedom. For our problem, we have support degree of freedom at node 1, node 2, 7 and 8. That means, because of this, that means we need to add a last stiffness at 1, 1, 2, 2, 7 and 8, 7, 7, at this position, and at this position. So we need to modify this value by adding a large stiffness to this position. So that's what I did in my next slide. I didn't actually show it. For this, I didn't show for this, I wrote a code. The code is not shown, but the code, let me write it here. K, open bracket, 1, 1 is equals to infinity. You can write it in infinity. You can write it in this manner. But remember, infinity. Remember, I actually created a stiffness for each of the degree of freedom. K1R equals to infinity. So I can actually write I can actually write K1R. So as you run this line of code, you will see infinity is added to this position, which is what I want, a very large stiffness called infinity. So for the second, for 2,2 at 2,2 of the global stiffness matrix, I also added infinity. K2R is also defined as infinity. So once I run this code, you can see infinity is added at 2,2 of the global stiffness matrix. The same thing for at 7,7 of the global stiffness matrix. Where is the infinity value? 7,7. 1, 2, 3, 4, 5, 6, 7. This is it here, infinity. So this line of code, case 7,7 equals to K7R at infinity at 7,7 of the global stiffness matrix. At 8, 8,8 of the local stiffness matrix, I also added infinity. So these are my four. These are my, also added infinity. So these are the 4 infinity values I used to modify the global stiffness matrix. So this is my final modified global stiffness matrix, a 12 by 12 matrix, which we need to find the inverse of the 12 by 12 matrix. This is not a problem with Matlab. Matlab can easily compute an inverse of an 100 by 100 matrix. It's not a problem for Matlab. So we shouldn't be concerned. So our final modified stiffness matrix, which I define as K, is given as this. Like I wrote it 2 times actually. Like this one from 1 to 12, 1 to 8, because this local stiffness matrix is only showing from 1 to 8. I repeated the code to show the remaining 9, 10, 11, 12 rule. So this is the modified global stiffness matrix, the 12 by 12 matrix. So now we have defined the global stiffness matrix. The next thing we need to do, we need to define our global global force vector. This is actually wrong. We need to actually define our displacement vector, but to do that, we first need to define our force vector. And in this question, we have 3 forces in the question. We have for 0.5 kilonewton, we have 2 kilonewton, and we have 1 kilonewton. Our force vector will be a 12 by 1 matrix because there are 12 degrees of freedom. If there are 6 degrees of freedom, the force vector will be a 6 by 1 matrix. So this question, this line of code defines our force vector. And you can see because at node 2 we have 0.5 kilonewton. And I told you that the unit for my force is in Newton. converted this Newton to 5,000 Newton. This force is pointing downward, so I take it as minus 500 Newton. And because this force is in the vertical direction, so, and it is at node 2, I need to, sorry. The 500 Newton force, because it is at node 2 and it is pointing in the vertical direction, in the direction of degree of freedom 4, it means that we have to add the minus 500 Newton at position 4 of the force vector. That is why this is written here. For the 2 kilonewton force at node 5, it is also pointing downward, which will be minus 2,000 Newton. And because it is pointing downward in the direction of the degree of freedom degree of freedom 10. So at position 10 of the matrix, we specify minus 2,000 Newton. At node 6, we also have minus 1 kilonewton, which is equivalent to minus 1,000 Newton. And because it is pointing in the degree of freedom 12 direction, because it is pointing in degree of because it is pointing in this degree of direction, in this degree of freedom direction, that is 12, that means we add minus 1,000 at position 12 of the matrix. So there are 12 values in this vector: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And at position 4, 10, and 12, I specify the force. At other nodes, because there are no forces at other nodes are defined as 0. So this is written as this, and I use this, if you should notice there is an hyphen here. This hyphen is to change the matrix to a column vector. So this vector is defined using this line of code: 0, 0, 0, minus 500, 0, 0, 0, 0, 0, minus 2,000. The remaining 9, 10, 11, 12 is not shown here, but it's already stored in the Matlab memory. So this is how we define our global force vector for this problem. So now we have defined our global stiffness matrix and our force vector. We can calculate our displacement vector for the 12th degree of freedom simply by inverting K and multiplying by PS. You can write it like this, or you can also write it like the normal way I used to write it: inverse K is also a Matlab code, inverse K multiplied by PS. PS is our force vector, which we define. So they work in the same manner. Either you write it K slash PS, or you write it like this. Our displacement vector is calculated as this: 0, 0, minus 0.0257 mm, minus 0.0971 mm, in that order. You can see at node 1 and node 2, we have support degree of freedom. That's why the displacement there is 0. Tells us that we are doing the right thing. At 7 and 8, we also have 0 as our displacement. At 3, 4, 5, 6, we have values. Also 9, 10, 11, 12, which is not shown here, we also have displacement quantity. So our displacement vector is a 12 by 12 matrix, but here it's only showing 8 by 1 matrix. The many 9, 10, 11, 12 is not shown in Matlab. Matlab can only show 8 row quantity at a time is the problem. Okay, I think in this slide, in this image, I showed the remaining. So this is the remaining parts. This is the remaining parts 9, 10, 11, 12. The remaining displacement quantity. So these are our 12 by 1 displacement quantity. So these are minus 0.0257. It means that in the degree of freedom 3 direction at node 2, we have the truss. Let me copy this image. Let's interpret this value. I think is important. At node 3, we have minus 0.0257. What does this value mean? This is minus 0.0257 mm. It means at node 3, this is the direction. It means this node moves horizontally to the left because it is negative. Because of this negative sign, it means that this node moves to the left by 0.0257. And at degree of freedom, at this degree of freedom, node 4 minus 0.0971, that is at node 4. Because of this negative value here, it means that the node moves downward. It moves downward by 0.0971. So this is what, so this node moves downward. So the resultant will be, if we were to look at it, resultant will be the node moves somewhere here. This node moves somewhere here. So this is how we interpret the value. The same thing for 5 and 6. 5 and 6 is the degree of freedom at 5 and 6 is the degree of freedom at node 3. So we can interpret the displacement quantity in that same manner. So that's it for the displacement quantity. For each element, we can define a displacement vector for each element. Because each element has 4 degrees of freedom, each element is defined by a 4 by 1 displacement vector. Like element 1, is defined by 1, 2, 3, 4. So I can extract the quantity in my displacement vector, which I just calculated. This displacement vector, my displacement quantity for element 1 is in this position. At 1, 2, the displacement quantity is 0 because I support degree of freedom. At 3, 4, it is given by these two values. So I can extract these values with this Matlab line of code. ds1 means my displacement vector for element 1. So ds1 column 4. So if we should run this code, our displacement vector for element 1 is created. This is our displacement vector for element 3. Element 3, the degree of freedom is 3, 4, 5, 6. So 3 column 6. 3 column 6 means 3, 4, 5, 6. So this is our degree of freedom for, this is our displacement vector for element 2. This is our displacement vector for element 3. Let me send this forward. For element 4, these are for element 4, this is our displacement quantity. For element 5, let me erase this. This element 5 here, displacement quantity is the degree of freedom is 1, 2, 7, and 8. So this Matlab line of code computes the displacement vector. You can see the displacement vector is a zero vector because all the degree of freedom support degree of freedom, which is correct. We have support degree of freedom at node 1 and node 4. For this is displacement vector for element 6. This is displacement vector for element 7. Computed using the Matlab code, using the numbering, using the degree of freedom numbering. Displacement vector for element 8, using the degree of freedom numbering. Displacement vector for element 9, using the degree of freedom numbering. For element 10, this is the displacement vector. Element 10 is displacement vector using this Matlab code. For element 11, this is displacement vector. So actually for element 10, let me bring this here. This is how we explain. This is element 10 here. Let me erase all this first. Just want to explain one of it so it will be well understood. This is element 10 here. So it's given, say this is element 10. At node 3, bring to at node 3. At node 3, this is the degree of, this is the displacement quantity. At node 3, this is the, no, not that. This is the displacement quantity. So in this direction, we have minus 0.0. I can't write it, it's equal to write, sorry, but in this direction, we have minus minus. So this node here should displace to this point. This node here for this part, this part is 9, 10 at this node. We have positive, so that means it's no this 0 plus 0.0261 is in the horizontal direction. That means it moves to the right positively and it moves downward. So that means this we have a node somewhere around somewhere around this point. So this element, which is defined with this node and this node here, is now in this position. My sketch is so bad. It's now in this position. So this is how the displacement quantity is interpreted from the Matlab solution. So the reason why I actually computed the displacement vector for each element is because it is needed to compute the reaction force for each of the elements, which is actually what I needed. And if you remember, I introduced some formulas to you in the beginning of my video where I said the area force of each element is given by the local stiffness matrix multiplied by the displacement vector. So you can see K1 is my local stiffness matrix for element 1, DS1 is my displacement vector for element 1. K1 is a 4x4 matrix, DS1 is a 4x1 matrix. So you can multiply this together. Once you multiply this together, you get your force component in the xy direction at each node. If I bring this image into view, for element 1 is in the horizontal direction. So assuming I define element 1 as this line, this is degree of freedom 1, degree of freedom 2, 3, 4. Because the element 1 is located between node 1 and node 2, and the degree of freedom are 1, 2, 3, 4. I start my numbering from node 1 because the arrow is pointing from node 1. So 1, 2, 3, 4. So horizontally we have a force of, it means that horizontally we have a force of 5.464 kilonewton. I say kilonewton because we have 10 raised to power 3. It's actually 5,463 Newton. So we have an horizontal force of 5.4674 kilonewton. In the vertical direction, it is 0. There is not any force, which is correct. So this is for node 1. For node 2, we have a force of minus 5.4634 kilonewton. Because we have a negative value here, that means the force in the x direction will point to the left, and the value is 5.4634. The same thing for element 2. If we multiply the local stiffness matrix with the displacement vector for element 2, we get our force vector given as this. I actually I have a sketch of this. With this for element 2, you can see the force at node 2 is 0.94 kilonewton at node 2. At node 2 pointing to the right, at node 3 pointing to the left, 0.94 kilonewton, which is what I have here, 938.996 newton, which equals 0.94 kilonewton in the horizontal direction. For element 3, this is the force computed using this Matlab line of code, and this is what is defined in this manner. This is in tension. The force at node 4 is minus 5.54, which is what we have here, minus 5.5366. At the other node, we have plus 5.536, pointing to the right. So this is in tension, this is in compression, you can see the force direction, this is in compression, this is in tension too. Let me put this here, bring this to the front. So for element 4, this is the force vector computed using this Matlab code. For element 5 is a zero member. Element 5 is a zero member without any force here. If we use this Matlab code, we get 0, 0, 0, 0. Did I define element 5 here? Element 5, you see, element 5 which is here, I didn't define any force, I didn't put any force on the node, as you can see. For element 6, the force is computed and is defined in this manner. For element 7, the force is computed and defined in this manner. For element 8, this is for element 8 here, task forces in all the degree of freedom position. Element 8, let me try to explain this. Element 8 is given by this. This is element 8. This is element 8, and because the arrow is pointing from node 2, it is the numbering is 3, 4, 7, 8. So this is 3, this is 3, 4, 7, 8. So actually the resultant of this node 3 and 4 is the resultant force at node 2, while the resultant of the forces at degree of freedom 7 and 8 is the resultant force at node 4. So this is what we have here. Actually define each of them. So you can see the force defined. The resultant force will be something like this, because the two forces here are pointing outward. The resultant force at this node 2 will be something like this. You can find the resultant by calculating the square root of the square of this number and this number. Same thing with at node 4. For element 9, the force vector is given by this, and it is also defined as this. These elements, because the force is pointing in this direction, the resultant will be like this. The resultant will also be like this. So this element is in compression. This element here is in tension. For element 10, this element 10, the resultant will be like this, which is very easy to compute. So this is a tension member. For this member, the resultant will be like this. The resultant at node 6 will be like this. So this is a compression member. All the force vector I computed in this slide. Going to front, so you can see this for element 9, this for element 10, and this for element 11, and they are all defined with this sketch. When I use another program to verify the finite element procedure, I can't actually do this by hand because it's very, very rigorous. I actually use statically software to verify the finite element results. It was found that the displacement quantity for each, you can check it yourself. I'm not going to dwell on this. This is a table for the displacement quantity from statistical software. This is a table for the forces in the x and y direction from statistical software. It was found that the results were exactly the same. So it's as if statistical 2 is also using finite element procedure for truss analysis. So This is the procedure. This is how we use Matlab to solve plain source problem using the finite element procedure. And before I end, let's go to the Matlab environment and let's see how we actually implement this on the Matlab work environment. Yeah.